Yo ho ho! Over the past week or so, we have seen limits in this form several times. The limit as n approaches infinity of the sum as I ranges from 1 to n of f of x sub I delta x, with delta x equaling b minus a over n and x sub I equaling a plus I delta x. We have seen these sorts of things several times when we compute areas. And note that the sum, not including the limit, but the sum here is a Riemann sum. I want to say that a couple of times in different lessons so that we get used to that vocabulary. Those sums, those approximations of areas are called Riemann sums. We've also seen that something similar arises when we try to find the distance traveled by an object, if we know a bit about the velocity. And in Calc 2, you're also going to see that these sorts of limits of sums arise when we try to find the length of a curve, the volume of a solid shape, the center of mass of an object, the total work completed in different scenarios, and many other quantities. This is actually something that comes up in so many different contexts, and because of that, we're giving it a special name and notation. Boing! We actually call limits like this the definite integral of f from a to b. We call these integrals, and they are specifically definite integrals. You will see indefinite integrals later, but the definition here is the definite integral of f from a to b is written like this. We've got this kind of, squiggly sort of vertical line thing. It's an integral sign. I'm trying to describe it and not having really good words, but we have an integral symbol. And the function that we're dealing with, f of x, goes to the right of it. And then we put dx to basically mean that we are dealing with x. X is the variable, the independent variable for that function. And the limits are a and b. Those are the left and right-hand sides of the interval that we're looking at. And basically, this is a shorter way of writing the limit as n approaches infinity of the sum as I ranges from 1 to n of f of x sub I star delta x. It's just a more compact way of writing a limit in this form. So that is the definite integral, provided that this limit exists and gives the same values for all possible choices of sample points. If it does exist, we say that f is integrable on the interval from a to b, meaning we are able to integrate. All right. I'm going to go through this notation once more really quickly. We call this whole thing an integral. This is an integral sign or an integral symbol. The numbers that go at the bottom and top are our limits of integration, the lower limit and the upper limit. And those simply correspond to the endpoints of the interval that we're looking at, right? We were looking at the area underneath a curve between two x values. We were looking on an interval. When we were looking at the problem of trying to figure out the distance traveled with some information on velocity, we were looking at an interval of time. So these just give us the endpoints of that interval. They just define that interval. The procedure here, the procedure of actually calculating this is called an integration. And the f of x, the thing that we're trying to integrate, we call that the integrand. We are going to get more and more practice with this, and even though it seems new and confusing right now, you're going to get more comfortable with it as we deal with it again and again and again. When people ask me, what are the main things that are covered in calculus? What are the fundamental ideas? One of them is the derivative, which we've learned a lot about. We know that it kind of came from wanting to know the slope of the tangent line to a curve, to the graph of a function. And the other big thing is integrals. And integrals, which we have here, come from trying to find the area underneath a curve that's given by a function. So derivatives and integrals are kind of the two most quintessential things that you learn in calculus, the two big units, the two big tools that you learn, derivatives and integrals, differentiation and integration. And right now we are looking at integration. Now, I want to say a couple more things about this. One is that when we evaluate an integral like this, the result is going to be a number. It's not going to be a variable or an expression. The result is a number, which shouldn't be a big surprise because when we were evaluating these limits of sums, we were using them to calculate the area underneath a curve, and that was a number. You'd get a number as a result. The area is 1/3. The area is 15.3 repeating, whatever. And so the answer here is going to be a number, so it doesn't actually depend on the variable we use. In fact, we could use any other variable. If we have the integral from a to b of f of x dx, this is actually the same as the integral from a to b of f of t dt, or the integral from a to b of f of r dr. So we could be looking at our integral with respect to x. We could be integrating with respect to time. That's something we're going to see when we're looking at velocity and position and also acceleration. You might also be integrating with respect to a radius of something, perhaps in physics. The point is, it doesn't have to be a function of x. We are allowed to do this as a function of t, as a function of r, as a function of any other variable. And the variable doesn't really matter as far as the answer is concerned, because the answer is just going to be a number. And then there's one more thing I want to say here. We mentioned the terminology Riemann sums earlier. And I just want to say kind of one thing, picking apart the difference between an integral and a Riemann sum. So a Riemann sum is the sum part without the limit. Okay? If we're thinking about this in the context of finding the area underneath a curve, this is the approximations that we did, adding up the areas of several rectangles. And the integral is what we get when we take the limit as n approaches infinity, as the number of rectangles approach infinity. So what that means here, so this part is the Riemann sum. The Riemann sum gives us the approximation for the area under the curve, the approximation for the total distance traveled. And the integral, on the other hand, is what we get when we take that limit. The integral gives us the exact area under the curve, or it would give us the exact total distance traveled. So we do a Riemann sum first as an approximation, and then we use more and more rectangles, or we use more and more subintervals. And as we take that limit as n goes to infinity, that gives us the integral, which gives us the exact answer. It's a small but important distinction between those things. I want to make sure everyone understands what we mean when we talk about a Riemann sum versus an integral, because there is a difference there.